Influence of fossil fuels on the environment. There is now general acceptance that the burning of fossil fuel is having a significant influence on the global climate. Effective mitigation of climate change will require deep reduction in greenhouse gas emission, with UK estimate of 16 to 80% cut being necessary by 2050. Still paired with the nuclear power, this last leaves behind dangerous wastes for thousands of years and risks contamination of land, air, and water. This figure shows the catastrophic nuclear in Japan. There are several types of wind turbine for electric power production in the term of design. Electrical machines, different type, vertical or axial axis, or in the term of their placement offshore or in the land. The first development is in 1970 and the first development is since 1990. The average annual growth rate of wind turbine installation is around 30% during the last 10 years. The European Wind Energy Association has set a target to satisfy 23% of European electricity needs with the wind energy by 2030. We can classify the wind turbine by three types. The first type is fixed speed wind power is directly connected to the grid. The second type is variable speed wind turbine using a double fed induction generator or single cage induction generator. The third type is also a variable speed wind turbine but is based with permanent magnet synchronous generator. There is two major reasons to using variable speed, such as the reducing mechanical stress and optimized power capture. The advantage of using double-fed induction generators. The first one is the power electronics equipment only has to handle a fraction between 20 and 30% of the total power system power. The power electronics equipment can be reduced using a smaller converter. The inconvenience of using permanent magnet synchronous generator is inherent cooling torque, stop wind turbines, starting noise and vibration because of the magnet attractive forces. The second one is the risk of demagnetization because of the fault happening and overheating of the magnet. For double-fed induction wind turbine based on double-fed induction generator, we can say if the generator operates above synchronous speed, the power will be delivered from the rotor through the converter to the network, to the grid. If the generator operates below synchronous speed, then the rotor will absorb power from the network through the converter, as shown in the figure 2. Comment nous avons obtenu le modèle élément fini? La première étape, c'est de dessiner la géométrie. Deuxième étape, c'est l'association des matériaux, des propriétés des matériaux à chaque région, les conducteurs, les isolants, les fluides magnétiques, l'air, etc. L'étape suivante, c'est associer des sources de tension et de courant, les pertes, etc. Les conditions limites. Ensuite, on fait le maillage d'une manière intelligente ou dans les parties non importantes, on fait un maillage non fin et dans l'entrefer, on fait un maillage fin pour rendre le modèle plus fin. Parce que dans l'entrefer, la conversion d'énergie. Ensuite, la dernière étape, c'est le réglage de serveur, temps de simulation, le début, le fin, les pas de simulation, les relatifs, etc. Et dernière étape, c'est on dessine les résultats. In this slide, some of parameters of the double-fed induction generator are given. As example, the stator slot, the rotor slot, the output power, the right voltage, etc. This figure shows the 3D view of the double-fed induction generator with external rotor. This is the rotor and this is the stator. This figure shows the mesh of the double fed induction generator, the rotor, and this the starter and the rotor. In this slide, we would like to see the influence of the environmental thermal condition on the efficiency speed characteristic, where the efficiency is a function of speed of the rotor, and that means the wind. For this, several simulation has been carried out, and we compute the characteristic, the speed, the efficiency speed characteristic for several temperature, and this is the result of this computation. This figure is a zoom of this. We can see this influence. In this slide, we give some dynamic curves. The figure 8 gives the torque of the double fed induction generator of the outer rotor with outer rotor, and we can see that the torque has a value in the steady state average minus 33.75 Newton meter, and this figure gives the double fed induction generator starter current, and the steady state value is average 2 ampere, and the frequency is equal to 50 Hertz. In this slide, we represent the two different losses. There are two types of the standard losses quantities: standard losses and standard losses R. The standard losses represent the resistive losses in the 2D and 3D volume and is calculated by this equation, where J is the conductivity of the material. Standard losses R represent the losses based on the current time the resistance. Figure 10 illustrates two types of loss, where the value of standard losses in transient state is 355 watt and stabilized at 25 watt in steady state, but the standard losses is constant at 14.3 watt. The figure 12 shows the double fed induction generator stator current, stator and voltage, and rotor induced voltage, where the value of stator is 155 volt, but the value of rotor induced voltage is only 25 volt, as represented in this figure. The following figure shows the rotor current and the stator voltage of the double fed induction generator. The magnitude and the frequency of the first one is 7.12 ampere, and the frequency is average 50 Hertz, and the second one is 180 volt and the frequency is 50 Hertz. Field results in 2D of the finite element model. The finite element model of electromagnetic field is built by Maxwell 2D. This simulation is obtained by a PC with these characteristics: CPU, RAM, etc. Our model of double fed induction generator with external rotor used in the Maxwell environment has 12,154 triangle. The figure 13 shows the free distribution of double fed induction generator at 0.5 seconds. The figure 14 illustrates the free line and the contour diagram of the flux density. However, the figure 15 illustrates the total losses of double fed induction generator. This figure shows the free distribution of double fed induction generator at 0.5 seconds, and this figure illustrates the free density of double fed induction generator magnetic form at 0.5 seconds when the max is equal to 1.47 Tesla. This figure shows the total losses of the induction generator. In this part, we illustrate how we obtain and simulate the different case of number interturn for circuit fault double fed induction generator. We create several files with the same geometry, but each file has a specific fault. When we see that the machine, the rotor, stator, this parameter, the winding, the excitation, and the simulation. The transient simulation as function of time, and the 2D result is 2D. We create 6 files and simulate each case separately, and we use MATLAB Simulink to regroup each type of result to well see this effect. The simulation result. In this section, we present the simulation result of healthy and different case of interturn short circuit fault in phase A of the starter winding. We simulate the double fed induction generator with a different case of number of interturn short circuit fault in order to show well the effect of the number of interturn short circuit fault on double fed induction generator performances. Starter current of the phase A. Figure 20 demonstrates the comparison of the current of the phase A in healthy and in under different number of interturn short circuit fault, and figure 21 their FFT comparison. We can see that when the number of interturn fault is greater, the current has a higher peaks, like in this case. The following figures show the FFT of the phase A current in the healthy and under different number of interturn fault condition. We can see in black the healthy has only the fundamental and the magnitude of 2 ampere. But if the number of interturn fault circuit is greater, a peak, a magnitude of current is greater, and we see a different harmonic like represented in this figure. We can see the peak and the harmonics like represented in this figure. In this slide, we would like to illustrate the effects of the interturn fault in the phase A on the phase B and C. This phase is healthy, but in the current we can see this effect. The figure 22 shows the starter current of the phase B in the healthy and under fault different fault circuit fault condition in the phase A, not in the phase B. The phase B and C are healthy. We can see that the phase B, the phase A has an effect on the phase B, and when the number of entered fault circuit is greater, we can see these peaks in the current. Also in the phase C, but the phase C is less affected by the fault in the phase A. In this slide, we would like to show the 2D magnetic field. Figure 24 gives the distribution of the magnetic flux density for the healthy and faulty double-fed induction generator in different cases of number of undertone short circuit fault. When the phase F is healthy and the phase, as example phase E, we have 4 interturn fault circuit. The D result has only 12 interturn fault circuit, etc. We can see this result. As a conclusion, the finite element analysis is a frequently used method for analysis of electromechanical converter as a numerical analysis method. Finite element analysis allows for including any practical material, external excitation, voltage driven or current driven, inclusion of motion, and nonlinear effects such as magnetic saturation and eddy current effect, like in our model when we take into account the eddy current and the magnetic saturation and the motion. A 2D model of the double-fed induction generator with external rotor is given, solved. Some simulation result was given and commented. To return our simulation result finer, a 3D model is developed and solved, but the resolution time is very large. This time is a scale of the days. This model, 2D and 3D, obtained by using ANSYS finite element software. This last can be used as an effective way to design and calculate the double-fed induction generator performance. This work is the necessary preparation for design and development, higher reliability and higher security of double-fed induction generator application. As perspective, we perhaps do this work: parameter optimization, number of starter, etc. Double-fed induction generator diagnosis using FEM, a free software. Metaphysics modeling of double-fed induction generator, thermal, acoustic, vibration, etc. Control of double-fed induction generator, Maxwell sampler. Finally, we thank you for your attention. شكرا لكم. Merci pour votre attention.